As I said, I'm going to start from the simplest possible problem. And to start from something very simple, we need to make assumptions. A lot of assumptions that are going to, very restrictive assumptions that are going to simplify the problem. Let us assume that the universe we live in is one-dimensional, so that everything is happening in one dimension. So, for example, everything is happening along the axis of this line. The world is one-dimensional. And then for that to happen, you need to assume that uniform cross-section, basically the cross-section here is not changing. And you link everything happening within the line to what happens at the nodes. So you basically define the line or define the element. Here we are going to develop our first finite element, define it to what happens at the two nodes. Now, because this is a one-dimensional problem, the displacement are going to happen only in one dimension. So this node can either move in this direction or in this direction. And this one can also do the same. It is within the line. And at the same time, if you have any forces applied, the forces are going to be axial forces. So the force is going to be applied at the node, strictly at the nodes, and is going to also be applied within the same axis of the line. So it's going to be within the axis of this line. You see? So we are making quite some assumptions, restrictive assumptions here. We have a one-dimensional problem. So basically, the forces and the displacement would happen in one dimension, the axis dimension, and the element will have a uniform cross-section, otherwise it's not going to be one-dimensional. And then we restrict everything to happen within the element to be reflecting what happens at the nodes. So what happens at the nodes will define how the element is going to behave. All right. So these are the most important assumptions we make. All right. So we started from this assumption. We are going to build our first element. So we have this element here, move it here. And we are going to define everything in terms of what happens at the nodes. So let us first of all assume that the length, and excuse my handwriting is not the best. So assume that the length is L. So the distance between node 1 and node 2 is L. And we have the axis X to be the axis that define the coordinates within this element. And the displacement is U1. And here the displacement is U2. Now what I'm interested with, to start, I'm interested in defining the displacement anywhere along the axis based on the displacement at the nodes. So I'm going to write the displacement as an expression as a polynomial, as a first order polynomial. I'm going to define the displacement to be just a line. And then I'm going to define this line based on the displacement at node 1 and at node 2. All right. So basically, I'm assuming that the displacement is going to be some U1. I'm just going to draw it here. So this is, let us assume that this is U1. And then probably this is the element. And then you have probably another displacement U2 here. U2 is slightly larger. So you have U2 here. Then the displacement within the element would be defined across this line. So if you are interested in finding the displacement here or here, you can use the equation of the line to identify the displacement at any point within the length of your element. Now, this is a line equation. I'm going to define the line equation based on U1 and U2. So I can use the U1 and U2 to define the equation of the line. I can assume that at X equal to 0, this is node 1, and this is X equal to L, this is node 2. So at X equal to 0, I have U to be equal to U1. Right at this place here, right at this place, I have U to be equal to U1. And then this line equation will be AX, X0 plus B. Now, if you look into this equation, you will see that B is equal to U1. So you can basically write B is equal to U1. So you have been able to identify the first entry in your equation. The second one, we can use the second point. So this is at X equal to L. We have U to be equal to U2. And this will be A multiplied with L added to B. Now B, we already know this is equal to U1. So I'm just going basically to delete it. and replace it with u1. Now, if you look into this equation, you have everything except for a. So you can write al is equal to u2 minus u1, or divide everything by l, and this way you get rid of this l here. A equal to u2 minus u1 divided by l. Now I'm going to take this back into the equation and rewrite the equation. So you have ax. So you have u to be a. Now you have the expression for a. This is u2 minus u1 over l. u2 minus u1 over l multiplied with x, added to b. So this is b equal to u1. So it's basically going to be u1. Now I'm going to rearrange this so that I have everything to do with u1 first, everything to do with u2 second. So u1 exists in this term here and in this one. So I'm just going to put them together. I have u1 minus u1 multiplied with x over l. And then I have u2 multiplied by x over l, added to u2 multiplied with x over l. This is the expression for u. Now I'm going to take u1 as a common factor. So you have u1 multiplied with 1 minus x over l. And then you have u2 multiplied with x over l. Now I'm going eventually in the finite element method, I'm going eventually to work with matrices because I'm going to write everything into a code and implement everything on a computer. So to be able to implement things in a computer, the only way is to develop arrays or basically matrices. So you need to work with matrices. When you have this many small problems, you need to combine them within a matrix. So this is why you need to write down things in matrix form. So I'm just going to write this expression here just as a matrix form. So I'm just going to write here u is equal to 1 minus x over l. And then I have x over l. This is a row matrix. This is the row. And then I have a column matrix. So this is u1 and u2. Now, if you multiply the row with the column, you multiply this entry with this one and this one with this one, you get back exactly the same expression, which is where you started. Okay, so this is exactly the same thing. It's just written in matrix form. Now I have an expression for the displacement. I want to have an expression for the strain, an expression for the stress, and an expression for the forces, and I combine everything together, and then I have a definition for my problem. All right, it's basically any problem. When you link the forces to the displacement, you have a definition for your problem. You can solve it and identify the displacement or identify the forces. If you know the displacement, you can find the forces. If you know the forces, you can find the displacement. This is basically what you do in any mechanics problem. Now, if you have the displacement, obviously you can define the strains. And if you define the strains, you can easily define the stresses. It's basically, you know everything you want about the problem, starting from the displacement. All right, so back here, I have the expression for the displacement. I need to find an expression for the strain. So the strain is basically the derivative of the displacement. It is the derivative of u with respect to x. Now, I have this expression for the displacement. I'm going to differentiate this with respect to x. u1 is a displacement at the node and is not dependent on x. u2 is also the same. 1 is also not dependent on x, is a constant number. The only thing that is dependent on x is minus x over l and x over l here. Right? So if you differentiate this, I'm basically going to split it into u1 minus u1 xl plus u2 xl. So if you differentiate this, this is going to 0. If you differentiate this, you have minus 1 or minus u1 over l, where x, the derivative of x is 1. And then you have u2 over L. The derivative of x is again 1. All right. So the derivative of the displacement with respect to x is basically this quantity in here. And I'm going to write it in matrix form. Again, I have minus 1 over L. This is the first entry. 1 over L. This is the second entry multiplied with U1 and U2. All right. So I have an expression for the displacement and I have a second expression for the strain. I need to find also an expression for the stress. So sigma is the elasticity modulus multiplied with the strain. So it is basically the elasticity modulus multiplied with this expression. Now, in general form, you can have something else. You don't have elasticity modulus. If we're talking about two-dimensional problems, this relation is going to be more complex. And if we're talking about three-dimensional, this is going to be a three-dimensional. So this is going to be a matrix, which basically have a lot of details about the material properties. And we call this relation between the stress and the strain as the constitutive relation. But since we are living in this one-dimensional world, everything is so simple, and the relation between the stress and the strain is defined through the elasticity modulus. So you have the elasticity modulus multiplied with minus 1 over L, 1 over L, multiplied with U1 and U2. Now I'm going to pause for 1 second. I'm going to highlight this matrix here, because this is quite an important matrix. So this is the matrix which defines the derivative of the displacement. And this is a key matrix in the finite element method. Now, it is so famous to the extent that it has a name. So the name of this matrix is matrix B. It is always the derivative of the displacement with respect to the coordinates, with respect to x. It is always that. And it has a name. It is called matrix B. So if you want, you can write the strain in relation to matrix B. I mean, instead of writing the full thing, you can just write the strain is equal to B multiplied with U, where U is U1, U2, and B is minus 1 over L, 1 over L. And the stress is going to be elasticity modulus multiplied with B multiplied with U. All right. Do you have any questions about this? And then you have U is basically 1 minus x over L multiplied with U. And this is basically the summary for what we have done in this first sheet. Expression for the strain, the stress, and the displacement, and everything is linked to the nodal displacement here. So everything is linked to the nodal displacement. Now, apart from that, I have nodal forces. So I have the forces which are applied at the nodes. Now, the most general case is you have a node, or you have a force applied at node 1 and a force applied at node 2. So I'm just going to write that in matrix form. So I'm just going to write it as P1 and P2. So I'm just going to call this the matrix for the forces. Now I need to link, I'll just take these expressions here and move them here. And I'm going to link now the displacement with the forces. Okay, so this is what I'm going to do next. Now to link them, which will work. Which states that the external virtual work is equal to the internal virtual work. Okay, so what is the internal virtual work and what is the external virtual work? I'm sure you saw the principle of virtual work, but I'm going to quickly explain it. So if you have a body in equilibrium, you apply some virtual displacement. This is virtual displacement. It's not real displacement. I'm just going to probably apply some virtual displacement U1 hat, and then probably a smaller displacement here, U2 hat. Then the equilibrium will only be preserved if the work done by the external forces, which is this force here, and this force here, is equal to the work done by the internal forces, which is the stress multiplied by the strain resulting from this displacement there. All right. Now, this is basically the external force, the virtual displacement you had multiplied with the forces we have already on the problem. And then you have the strain, virtual strain multiplied with the stress, the actual stress integrated over the volume. All right. So I'm basically just going to write this expression and expand it. This is what I'm going to do here. So you have the virtual displacement multiplied with the force, and this is matrix. I'll probably just use a line to express a matrix here, and this is a matrix, is equal to the integral over the volume for the strain, virtual strain, multiplied with the stress. And this is transposed. This is transposed. Now, the transpose of a matrix is when you shift all the rows and you make them columns, and all the columns, you make them rows. I need to check the quiz to see how many of you have been able to know what is the transpose of a matrix. I'm just going to explain it here quickly. So if you have a matrix, A and B, this is a column matrix. You want to transpose it, and this symbol is for the transpose. This will result into a matrix A and B. So you take the first column and you make it a first row. Now, if you have multiple rows and multiple columns, then the resulting here will be the first column will be a first row, and the second column will be a second row. So this is the transpose of this matrix here. Okay, so in order to be able to multiply the forces and the displacement, you see that the displacement is also a column matrix. So you need to have the transpose of that. All right, you cannot multiply two matrices. So in this case, I'm going to expand these terms in there. Oops. So I have a virtual displacement. I'm just going to write it down. This is U1 hat, U2 hat, multiplied with P1 and P2. This is equal to the integral. Sorry, this is dV in there as well. So this is equal to the integral over the volume. I'm going to write this down as an expression for what I had in the past for displacement. So I have B multiplied with U. I'm just going to write down that. And for the stress, I'm going to write elasticity modulus multiplied with B multiplied with U. So this is B multiplied with U. And this is the virtual displacement, because this is a virtual strain, and the whole thing is transposed. And then we have the stress matrix. This is the elasticity modulus multiplied with the B matrix, multiplied with the displacement over the volume. Now, the transpose of a multiplication is this is math. So you switch the location and you find the transpose of individual matrices. So then we have the transpose. As I said, the transpose is going to be just switch this two matrices and apply the transpose of each one of them individually. So this is the transpose of U hat, and this is B transposed multiplied with E, multiplied with B, multiplied with U, dV, and this is the integration over the volume. Now, if you look into this side here you have the P and the U hat transposed. So you can basically cancel the virtual displacement together. You are only left with the forces on this end, and you are only left with the displacement on this end. So you have a relation between the force and the displacement there. You need to expand this in order to define the displacement or then define the relation. But once you expand this expression in there, you can basically find the details of the relation between both things. So I'm just going to expand the matrices now. So this is P1, P2, is equal to the integral over the volume. B transpose is minus 1 over L, 1 over L. And the elasticity modulus is constant. I'm going to take it outside the integral. You have minus 1 over L, 1 over L. And this is multiplied with U1, U2, the volume. Now, the multiplication of a column with a row is basically this entry multiplied with this entry. We put it in there. This entry with this one, we put it in here. And the same is for the second row. So this one multiplied by this one is 1 over L squared. This one multiplied by this one is minus 1 over L squared. This one by this one is minus 1 over L squared. And this one by this one, this is 1 over L squared. So I can now take the L. I don't need these anymore. I'll just remove them because I've already multiplied them. And I'll shift this whole thing. Oops. Shift it here. And then I'm talking about the integration over the volume. Now, if you remember, when I mentioned the bar, I mentioned that the bar has a constant cross-section. So the cross-section is not changing and is constant throughout the length. So the integration over the volume can be replaced with an integration over the length if you take out the area. Which is basically the integration over the volume is calculating a volume, and the cross-section multiplied with the length is going to give you the volume. So I can remove this one in here. And replace it with an integration over the length, so between 0 and L. And this one here will be integration over the length instead of integration over the volume if I take A as the cross-section and put it here. So I have A multiplied with the elasticity modulus, and then the integral of these quantities. Now, again, this L squared is a constant, so I'm just going to take it outside. Just going to write it down here. E A over L squared, integral between 0 and L, 1 minus 1 minus 1 and 1, multiplied with U1, U2, dx. And in fact, if you look into U1 and U2, you'll see that these are also not dependent on x, so you can take them outside the integral, which is something also you can do. I'll probably just So I'm just going to take them outside the integral. And the integral will happen only on these constants. So it's basically integrating 1 between 0 and L, minus 1 between 0 and L, minus 1 between 0 and L, 1 between 0 and L. And the integral of 0 to L for 1 dx is going to be x between 0 and L, and is going to be L minus 0 and is equal to L. So basically, you can replace these constants here with ones. So I can get rid of the integral sign. I replace these ones with L's. So this is L minus L minus L and L. I just put them closer together. Now I have a relation between the displacement and the forces, and this is the relation between both. And this is what we call the stiffness matrix. It has a name. It's called the K matrix. All right, so you are integrating for the volume is basically going to give you the volume, all right? So the integral over the volume is just to define a volume. It's just like the integration over an area will give you the area, or an integration over a function. This is fx, and this is x. So if you are integrating between x1 and x2, you basically trying to identify the area here. The same thing if you are integrating in 3 dimensions. If you are integrating a function, you are defining the volume of this function. Now the volume, if you have a cross section here, or probably just put here for a line, and then the cross section of this line is constant. So you have basically a bar. The cross section of this bar is not changing. And you are trying to integrate over the volume of this bar. So basically you're taking a slice and you're moving the slice across the entire length. Now this is going to result into the volume. Now this can be exactly the same as if you take the area of this slice, the area of the cross section, and you integrate over the length. All right, so to understand this a bit better, I'm going to solve an example. Okay, we said that with finite element method, we divide a big problem into many smaller problems. These smaller problems are quite simple, and we combine these many smaller problems into the big one, and we solve the resulting problem, and it solves the big problem. So first of all, I'm going to use this element, this very simple element we have developed. I'm going to use that to solve a simple problem. We start from a very simple problem. So we have a cantilever. The cantilever has a fixed end and a free end. And at the free end is loaded with a load W. The length of this cantilever is L. And I want to solve this using the finite element method. All right. So to solve this with the finite element method, I can use this relation which I've just derived. Basically, EA over L squared. Now, I can cancel these L's here with a square in there, and I will have EA over L. So, I mean, you can leave it on the outside or you can insert it inside. It doesn't really make any difference. So I can use these equations, or I can use these equations to solve the problem. Now, first of all, to solve the problem, I will write the relation between, I first of all divide the problem into elements. One element can solve the problem because I have the forces already applied at these ends here. I have a reaction here, and I have a force in there. And then one element can solve this problem for me. So this is node number 1, and this is node number 2. So this is the displacement at node number 1. This is the displacement at node number 2. This is the force at node number 1, and this is the force at node number 2. Now, if you look into this system here, you see that you have 2 equations. I'm going to write them down. P1 is equal to EA over L, U1 added to EA over L, U2, and P2 is equal to EA over L, U1. This is negative, sorry, and this is negative. Added to EA over L, U2. This is a negative sign here. So if you look into this, you'll see that you have 2 unknowns on the left. This is U1 and U2, and 2 unknowns on the right. So it's U1, P1 and P2. So in order to be able to solve these 2 simultaneous equations, you need to at least have 2 out of these 4, you have them known. So let us discuss these unknowns. Do I know the value of U1? Point. So the value of U1 is 0. How about U2? Do I know the value of U2? The value of U2 is unknown for us. How about P1? This is equal to the reaction. But at this stage, we have not solved the problem, so we don't know what is the reaction. We don't know what is the value of the reaction. All right. I mean, of course, using equilibrium, we can get the reaction, but at this stage, we have not solved the problem, so we don't know what is the value of P1. Now, how about P2? So this is equal to W. So I'm going to replace this inside the problem and solve. So you have P1 is equal to EA over L multiplied with 0. Sorry, is minus EA over L multiplied with U2. And you have P2 is equal to minus EA over L multiplied with 0 added to EA over L multiplied with U2. Now, in the first equation, we have P1, we don't know. We have P2, we don't know. In the second equation, we have P2 because this is the W. Whereas P1, we don't know. So in this second equation here, everything is known except for U2. So this is 0. We have U2 equal to L. We multiply everything with L. So this is WL and divide by EA. And then once we have U2, we can substitute back U2 into this equation. And then we have P1 is equal to minus EA over L multiplied with WL over EA. So the L will go away with the L, A will go away with A, E will go away with E, and we are left with minus W.
Minus W.
And P1 is equal to minus W, and this is the value of the reaction. So the reaction is equal to minus W. Now we have U1 is equal to 0, and we have U2 is equal to WL over EA. So I can find the strains and the stresses. If you remember here, here we have the expression for the strains and the stresses. So the strain is basically the B matrix multiplied with U. The stress is elasticity modulus multiplied with V multiplied with U. And we can find that. So I'm just going to use these to find them. So the strain is the B matrix multiplied with U. And the B matrix is minus 1 over L multiplied with U1 and U2. U1 is 0. And U2 is WL over EA. So this one multiplied by this one and this one multiplied by this one, we will have 0 minus 1 over L added to 1 over L multiplied with WL over EA. So the L will cancel with the L. We will be left with W over EA. So this is the value of the strain. And the stress is the elasticity modulus multiplied with the strain. So this is
W.
E multiplied with W over EA. So the E will cancel with the E, will be left with W over A, which is to be expected because if you look into this problem here, you'll see that this is the force applied and the stress is basically the force divided by the cross section. In the next case, we have a cantilever again. The cantilever is similar to the one we had in the past example. It's pretty much exactly the same thing. However, in this case, we have the cross section changing from 2A to 1A. Now, can we solve this problem using the finite element method? Or using the element we have already developed, the element I've just shown you, I've used for solving a problem. Remember that in this element, we have assumed that the cross section is fixed. The cross section is not changing. So can we use this element to solve this problem? So if I understand you correctly, Singh, you are talking about this integral here, a over dx, right?
Yes,
now, as you said, if the cross-section is constant, we take this constant outside the integral and we do the integration over x. But if this is not constant, we cannot replace the integration over the volume with the integration over the length. Then in this case, we need to perform the integration over the x and y and z. So basically, this would need to be replaced by integration over x, y, and z, dx, dy, and dz. So we need to perform the full integration then in this case. And then we develop the element. And the element we develop will result into some stiffness matrix. The stiffness matrix we can use then to solve the problem. So this is one way to solve it. Can we do some other ways to solve this problem? I mean, we develop a stiffness matrix and we can solve it using the new stiffness matrix. But can we do something else? Take the average area, but then if you have the average area, what sort of information you gain from solving the problem? Do you think the average area would result into the same displacement as if you have this tapered cross-section? Take the problem, we solve it first for 2a. So we take this a here, we take it as 2a, and we assume that the cross-section is 2a across the entire length. And then we solve for this 2a problem. And this will give us some numbers. And then we solve it again. For the second time, we use a as the cross-section. So we have a as the cross-section. So we actually solve two problems. One problem, we have 2a as the cross-section, a uniform cross-section, and the second problem where we have 1a as the cross-section. So we have two numbers. What information can we get that instead of solving this problem here, we solve two problems. So the first one, we have the cross-section equal to a, and the second one is the cross-section equal to 2a. In the first case, where we have the cross-section is equal to a, the element or the beam here is going to be weaker than the original beam. See, the original beam is quite thick compared to the a cross-section. And then in this case, because this cross-section is weaker, the displacement and this is the actual one. So the actual one, I'm going to call it a dash. Now, a is going to lead into smaller displacement than a cross-section, because a dash is stronger than a, whereas if we take the 2a cross-section, the 2a cross-section is going to be stronger than a dash. So always, this is going to define the absolutely maximum number the displacement, or the absolutely minimum number the displacement can be, and this is going to lead into the absolute maximum displacement number we can get. So we know for sure that the displacement is going to be, the displacement of the actual case is going to be within this range between a and 2a. So we identify a specific range where we know that the displacement is going to lie at. Now, as a designer, you can think about this in two approaches. So as a designer who are interested in the strengths of the material, where you want really to minimize the displacement, you assume A is the cross-section and you design for A. Whereas as someone who's going to be designing for the safety of the displacement, you probably will be taking the other case scenarios. Basically, as a designer, you really need to make a decision on what sort of cross-section you want to design for. Okay, so basically what sort of safety you want to add to your design. If you assume that this is your cross-section, this is not safe, but this will definitely give you the minimum displacement that could happen. And for some reason, if you are interested in finding the absolute minimum displacement, then this is what you need to look for. If you are designing for the material and you really want to assume that this is the weakest possible, now you'll be wasting a lot of material in there. But anyway, you know that your design is going to be safe. Okay, so this is up to you as a designer to decide on where to go with your assumptions. Basically, this is what we can use for the finite element. This is how powerful the finite element, or this is the, I'm going to exaggerate things a little bit here. So if you want, you can do multiple elements, just like Alexander suggested. So you have one element here, and then probably another element here, and then another element, and another element, and so on, up to the minimum cross-section. Now think about it. Each element will have a constant cross-sections, but this many elements would result into something similar to this. Now, if you divide it into 3 elements, only 3 elements here, this is going to be some sort of an approximation, but instead of using 3 elements, you can be using 20 elements. You can be using 30 elements. It's completely up to you. So you can really use enough element to represent the whole thing. And think about it this way. So basically use elements, as many of them, to the extent that you probably get beyond the machine precision. And then from the machine point of view, these many elements will represent this regular, this uniform change in the cross-section.